Hi there. This video is a recap of Unit 1. I'm going to talk about three things. One, this electromagnetic spectrum that you can see in this image here. Two, about Beer's law. And then the third is about periodic trends. So let's look here. So you can see this is the electromagnetic spectrum. In that spectrum, we've got different kinds of energy, and it does different things to the atoms. And this is about if you shoot a certain amount of energy into an atom, what happens to that atom? So, quick little recap. Here's wavelength. And then here's frequency, that's new. If I do C equals wavelength times frequency, that's one of the equations on your equation sheet, I can see that they're inversely proportional, meaning as wavelength goes up, frequency goes down. My frequency over here is really low or small, and my frequency over here is very high. My wavelength over here is very small, it's an inverse of the frequency, and very large or big on this side. So my wave kind of looks wavy like this, and it's more jagged on the other side. Now, what really matters about this isn't so much wavelength or frequency, but energy. Energy is equal to h, which is Planck's constant, times nu, the frequency. So there I can see that frequency and energy are directly proportional. If one goes up, the other goes up. And that's why I know that the energy over here is really high, high frequency, high energy, and the energy over here is very low. Now that matters when I'm talking about atoms. So let's say I take this amount of energy from whatever it is for frequency on up here. This energy, if you're shooting this into an atom, it's going to remove an electron. This amount of energy is where you got your photoelectron spectroscopy going on. Photoelectron spectroscopy is PES. PES is the idea that if you have an electron sitting around the atom and you kick it out, then you can see where it was located. Or if, let's say you want to kick out this electron, it'll give you those peaks. And that's how we can tell if it's 1s2, 2s2, 2p6, or whatever it might be for its electron configuration. So PES tells us electron configuration. Going a little different here, we've got the visible spectrum. The visible spectrum, this is when you're going to be dealing with Beer's law. What you did in first year chemistry, and it still applies here, is like you take a chemical and you put it in the fire and it would light a pretty color. Well, more often in AP Chem, what we're going to be looking at is Beer's law. Beer's law is when you use UV vis spectroscopy, or that's the colorimeter. Colorimeters are just cheaper than the spectroscopy, so that's why we use them in school. So that's when we can tell like how concentrated a solution is. That's what part 2 of this video is about, so you'll have to go to there. Infrared spectroscopy, that's when we're going to have vibrations of things. Vibrations of the bonds. Like let's say you have a C double C bond, or you have a C single C kind of bond. Well, each of these are going to vibrate a little bit differently because the bonds are different. How it shakes or moves about will be different, and you can see that in its spectroscopy. The final way is microwaves. Microwave is what they're going to do is like vibrate things or rotate them per se. Rotate's a better word here. It's going to rotate them, and that'll create friction, and that friction is what creates heat when you heat it up in the microwave. Now on the AP test, I think it's very unlikely you're going to see a question on this topic because it's more of a multiple choice kind of question. However, this sort of thing, you would just write it on your note card. We're going to be able to use the note card on the AP test, so I would just take your Unit 1 note card, boom, write this stuff on there. That's most important. Basically, like this chart is super important of what's going on, and then you can just reference it if it ever comes up. So that would be that. Looking a little bit more into Beer's law then, Beer's law is the idea that if I want to look at like these blue things, I can clearly see that this blue over here is a darker blue than this blue over here. And so I would say this darker blue is more concentrated. While in chemistry we want to know the quantitative value, in other words, we want a number from it. So Beer's law allows us to get a number. Now, there are two things you need to know with Beer's law. First thing is this thing on the right. So let's say we're looking at FeCl3. I'm coloring it in orange because that compound is like an orange-reddish sort of color. An orange-reddish color is what you see because the orange-red light is reflected back into your eyes. It goes through the compound. It isn't absorbed by the compound. So the highest absorbance of this one is sitting like right here. That's not the orange light spectrum. That's around like, I don't know, 485 nanometers for its wavelength. And the first thing you know about Beer's law is they might show you this chart and say, hey, what wavelength should you use? You would say, I would use 485 nanometers because it has the highest absorbance. You don't need anything fancier than that. I explained the fanciness on why this is when we were first learning it. But to answer it on the AP test, all you need to say is, I use 485 nanometers because it's the highest wavelength. Then, if we look over here on the left, you'd set your colorimeter to 485 nanometers, something close to that, and then you'd have your different colors of solutions, and you'd put them in the colorimeter, and you'd get out different absorbances. We can see that the higher concentration will lead to a higher absorbance, because you're not absorbing the same color you're seeing. Like this blue color here, if I put this into the spectrometer or the colorimeter, I would want to see how much does it absorb in its opposite side, like how much red does it absorb. Not how much blue, because it's not going to absorb much blue. I want to see how much red. So that's what's going on here. I get a high absorbance with a high concentration. A basic question that you might see, other than this one over here that we already talked about, would be this one down here. It says the absorbance of an unknown solution is 0.275. 0.275 sits right here. What's the concentration of the solution? You just got to read the graph. I'm thinking it's 0.050 molar. That's my units of concentration. That's what you need to do, is read the chart. I think this is totally something that you could have to do on the AP test. And then you take this molarity and you take it for there to solve some other problem. Maybe do some stoic with it or something like that. So that's that part. The last thing I want to talk about is periodic trends. For periodic trends, I wanted to recap this, how to write a problem. Now, when you're going to get a periodic trends question, it's really going to be 3 sentences or less. I got this information from a guy who writes and grades the AP tests, and this is kind of how he explains how to write things. 3 sentences or less. You just want to hit them. Don't keep talking and talking, because you'll probably talk yourself into a wrong spot, or you'll bore them to death, something like that. So keep it short. I'm kind of giving you an example here. Potassium has a lower first ionization energy than lithium. Well, I probably want to go to my periodic table and look for potassium and lithium. My potassium is right here, and my lithium is right here. So when I'm looking on the periodic table, I'm thinking a couple things. I'm thinking about size. Potassium is much bigger than lithium. I'm thinking about ZEF, effective nuclear charge. I can see it's in the first column here. Effective nuclear charge is basically like how much of the nucleus does the atom actually feel, the outer electron actually feel. And that's going to be equivalent to what your valence shells are. So this is like 1 valence electron, 2, 3, 4, 5, 6, 7. So this column here has a ZEF of a positive 1. Potassium and lithium are the same. So right there I'm thinking, okay, ZEF is the same, but the size is different. That's something indicative of things. I'm going to go back over to my sheet here. Okay, so if I'm going to write about things, the first thing you want to do is see what the difference is and state the reason for it, state the trend. I would say potassium, this one is the bigger one. This is your K, and lithium is I. This is smaller. I would hit about distance. I would say potassium is a larger atom than lithium. Boom, that's sentence 1. Sentence number 2, wait, okay. Potassium is a larger atom than lithium because, that's a key spot, I was thinking where I was going to put that, because potassium has more energy levels than lithium. Energy levels is the word you want to use, not just orbitals. So I would say potassium is a bigger atom than lithium because it has more energy levels. Second part, a greater number of energy levels means there's a greater distance between the nucleus and the electron. According to Coulomb's law, a greater distance corresponds to a lower attraction between the nucleus and the electron. Now I'm going into this part here. A lower attraction means you have a lower first ionization energy. I hope you can see how I've kind of tackled this. You're stating the trend, explaining the trend kind of thing. It's going to be distance, it's going to be ZEF, and if neither of those works out, then go electron configuration. That's going to be the reason for whatever they're explaining here. It's going to be one of those 3. I can't say it's going to be anything other than one of those 3. It'll be really tricky if it was something different. Not likely. Totally not likely this year. Then you're going to somehow apply Coulomb's law, and then come back to the question. The question came back to first ionization energy. So my end sentence was talking about, therefore, boom, first ionization energy. Think of it in like 3 big parts. Hit aside, apply Coulomb's law, make sure you're addressing the question somewhere. And that should kind of hit you home. Okay. So those are my 3 topics for you. That should do it. Okay. So what you're going to be working on is your note card. So make sure to make a killer note card for Unit 1. Like really look through all of your notes. Don't just do whatever I did on this video. Look through all of your notes, put it all into one spot so you know exactly what's going on. And then try some of these AP problems. What I want to end with is our journey. That's that goes through in the back. We're going to have to do the wheel decide here. So here, where's my thing? Here's my video. Okay, so to remind you, these are our 3 characters. We need to get them to the end battle, but first they need to set off all of the beacons. You can see that you want to park your boat, but the sirens are there. You got to get rid of them. So we'll decide. Dalton, the 4th hour. 4th hour, Team Dalton. It is your job to help us get past the sirens. You have to in some way sing. You can choose to sing or you can play an instrument. I know a lot of people have taken up guitar. So even if you're like just learning guitar as of this quarantine time and you've been doing guitar for like 2 weeks, we'd love to hear it. You could play Hot Cross Buns on a recorder. You could play Happy Birthday. You could play Itsy Bitsy Spider. You could sing any song you want or play any song you want or even lip sync something. But one of you from this Dalton 4 team, that's the minimum requirement, one of you has to produce some sort of something in a video form and send it to me and see if we can do that. If you choose not to, we'll just kill off one of our players and we'll still be able to go on because we'll have 2 of them. But we're also going to take the vote to see if it is good enough to take the sirens down. There you go. Good luck.